Hello student, myself Swapnil Sir and welcome to yet another video on vector chapter. Already we have started lecture series on vector chapter. Complete lecture series I explained on our vector chapter. Within that I explained some of the important theorem along with examples in our previous lecture. So if you wanted to see this video, you do check in my playlist. So already there are another topics, so I have uploaded in my channel like a pair of straight line, a trigonometric and another differentiation type of the topics I have uploaded in my channel. So if you are interested to see this video, do refer these videos. Okay, so in my today's video I'm going to explain to you all the vector chapter, basic concept from the vector chapter, which is the little recap video. We may consider this one. Okay, and after that we go for some of the questions solving, important questions solving from our vector chapter. Okay, so without further ado, let's get dive into our today's lecture. First of all, we go for some of the basic concept from vector chapter, and then at the end we move for our question solving based on our vector chapter. Okay, so now in our vector chapter we just need to know some of the basic concept like a collinear vector, coplanar vector, like when vectors are perpendicular, when vectors are parallel, how can we define the condition. At next part, we have defined here direction ratios, direction cosines. Okay, for finding the direction ratios, direction cosines, we have to use some of the standard result here. Okay, for direction ratios and cosines. After that, two vectors are perpendicular. If we have given two vectors are perpendicular and we want the value for our third point which divides our line segment AB, then how we can define our perpendicular vector. That things we are going to learn here in our today's lecture. Along with that, we are going to understand the meaning for perpendicular vectors and parallel vectors. Okay, and direction ratios, direction cosines, some of the standard result from the direction ratios and direction cosines we are going to see here. Okay, so what we start from here now, first of all we are going to understand one concept here, the parallel collinear vector and a coplanar vector. Okay, the collinear vector means the vector which are the parallel to each other. Okay, so that means the vector, consider vector AB and BC. If both vectors are parallel to each other, then we consider it as the collinear vector. If both vectors are perpendicular to each other, then we consider it as the okay, so there is some another condition for perpendicularity, but if vectors comes here as a perpendicular, then we cannot consider them under the collinear vector. Okay, the collinear vector, it says that vector A to B and B to C, vector A to B and vector B to C, both vectors need to be in a same line. Okay, so these are the collinear vector, or we can write the vector AB and a vector BC. The vector AB and a vector BC, both vectors are here parallel, then we consider it as the collinear. Okay, so if you wanted to show two vectors are collinear, then we consider one vector is a scalar multiple of another vector. Okay, that condition we prove here. After that collinear vector, the next condition here for the coplanar vector, the vector which lies in our same plane, then we consider it as the coplanar vector. There are some conditions that need to hold for the coplanar vector that we are going to see in our subsequent lecture. Okay, now in our next part we see here the section formula. Okay, the section formula, which is basically divided into the two parts, which is a internal division and external division. Okay, so before I explain here the section formula for internal and external division, so why actually we needed this section formula. Okay, so as we know that if we have line segment, any line segment, consider line segment AB, and that line segment AB divided by third point C. Okay, the line segment AB is divided by third point C, and we know that the ratio from A to C and C to B both are the equal. Okay, so consider both ratio are here equal. Then for finding the value of a point C, that means the midpoint of our line segment, we write A plus B upon 2 here. Okay, A plus B divided by 2, so which gives us the midpoint for our given line segment. Okay, so this one is the midpoint for our line segment, but instead of that midpoint, if we have the ratio m as to n, the distance from A to C and C to B which are not constant. Okay, like we consider A to C here, we consider here A to C and C to B. Okay, now we can see that here the distance from A to C which like a m and C to B which like a n here. Okay, so both distance are not not at all equal. Okay, so when we have these two distance not equal, then we have to use some another condition from the mathematics like a section formula for internal and external division. Okay, so there are two conditions that C point can divide our line segment internally, or maybe it can be divided at externally. Okay, so this one is the internal and external division for section formula. So internal division of a section formula, it says that, okay, internal division. Okay, section formula for internal division. Okay, that means the point which divide our line segment internally, we consider it as the section formula for internal division. Okay, yes, and we can write it as the m into a bar plus n into b bar upon m plus n, which is the section formula for internal division. Okay, and the division of that internal line segment AB, which is in the ratio of m as to n. Okay, now section formula for external division. Section formula for external division, we write m into a bar as a point it divides externally. So we take negative m into a bar minus n into b bar upon m minus n, which is a section formula for external division. Okay, so that's it here for our some of the concept we needed here for our next examples. Okay, after that we have some of the condition for finding the direction ratios, direction cosines. Okay, so for finding the direction ratios, direction cosine, we use some standard result like L square plus m square plus n square, which is equal to 1, and L can be represent here cos times alpha, m can be represent here cos times beta, and n can be represent here cos times gamma. Okay, cos alpha, cos beta and cos gamma are the value for L, m, n. Okay, that means our standard result can be written as cos square alpha plus cos square beta plus cos square gamma, which is equal to 1. That is the that one is our standard theorem. Okay, for it is helpful for finding the direction ratios for our line. Okay, for finding the direction cosines of our line, we define it as the a upon square root of a square plus b square plus c square. Okay, so this one is the first direction cosine. Secondly, we define direction cosine b upon square root of a square plus b square plus c square. Okay, and third direction cosines, we define it as the c upon square root of a square plus b square plus c square. Okay, these three are the direction cosines of our given vector. Okay, so let's see, we are going to apply all these result in our subsequent examples. Okay. Okay, so we have first example here, alpha, beta, gamma are the direction angles of the line L. Okay, so what we have given, let me write what we have given here. Okay, so alpha comma beta and gamma. Okay, these three alpha, beta, gamma are direction angles of the line L. Okay, are the direction, okay, direction angles. Okay, direction angles of the line L. Okay, so we have given alpha, beta, gamma are the direction angles, okay, of the line L, and we have to prove here cos square alpha, cos square beta, cos square gamma, which is equal to 1. Okay, so which is a cos square of alpha plus cos square of beta plus cos square of gamma, which is equal to 1. Okay, this one is our standard statement for theorem. Okay, cos square alpha plus cos square beta plus cos square gamma, which is equal to 1. We have to prove this condition here. Okay, so I proved this theorem in my previous video. So if you wanted to see this statement of the proof of that theorem, you do check in my playlist. Okay, you will get the proof of this entire theorem, because it's quite time taking, and already I have proved this one. Okay, so I don't think so we have to go for it again. Okay, so if you wanted to see the entire proof of this theorem, do check in my playlist. Okay, now here in our next attached question we have here, hence deduce that sin square alpha plus sin square beta plus sin square gamma, which is equal to 2. Okay, so what we have to find here, sin square alpha plus sin square beta plus sin square gamma which is equal to 2. Okay, this condition we have to prove it here. Okay, using cos square alpha, cos square beta, cos square gamma which is equal to 1. Okay, take this condition, apply some result and prove this one here. Okay, so by using this standard form of our statement, we are going to prove this condition here. Okay, now here we can see our statement is in the form of a cos square alpha, and our condition that we want here, which is given in a sin square alpha. That means we have to convert cos square alpha into the form of a sin square alpha. Okay, and we know that one more standard result that can be applicable here, which is a cos sin square alpha plus cos square alpha which is equal to 1. Okay, sin square alpha plus cos square alpha which is equal to 1. So if you want the value for sin square alpha, we can take it as the 1 minus cos square alpha. Okay, okay, so we can write first important result, sin square theta plus cos square theta which is equal to 1. Okay, by using this result we can write cos square theta which is equal to 1 minus sin square theta. Okay, or sin square theta can be written as 1 minus cos square theta. Okay, this condition, so we can write it here. Now what we do, substitute these values in our cos square alpha, cos square beta and cos square gamma. Okay, so cos square alpha, we know that cos square alpha can be written as 1 minus sin square alpha. Similarly, cos square beta can be written as 1 minus sin square beta, and third cos square gamma can be written as 1 minus sin square gamma. Okay, and right side which remain 1 as it is. Okay, okay, let's go for the substitution of the value. Cos square alpha can be written as 1 minus sin square of alpha. Okay, cos square alpha can be written as 1 minus sin square of alpha, plus cos square beta can be written as 1 minus sin square of beta. Okay, plus cos square gamma can be written as 1 minus sin square of gamma. Okay, which is equal to 1. Okay, this one is our little adjustment in our given standard theorem. Okay, so cos square alpha written as 1 minus sin square alpha, 1 minus sin square beta and 1 minus sin square gamma. Okay, now take similar term together and sine term of a sine together. Okay, so what we will get here, 1 plus second one plus third one. Okay, we have 3 times 1 here, minus of a sin square alpha minus of a sin square beta. Okay, minus of a sin square gamma which is equal to 1 here. Okay, this one is our next condition using our given data. Okay, yes, so using this condition, so let's move for the next calculations. We have 1 plus 1 plus 1 which goes to the 3. Okay, take that 1 to the other side, so 3 minus 1 we will get the, okay, so keep as it is. 1 plus 1 plus 1 can be written as a 3 here. Okay, so take negative sign common, under bracket it remains sin square alpha plus sin square alpha plus sin square beta plus sin square gamma. Okay, sin square beta plus sin square gamma. Okay, which is equal to 1 remain here. Okay, so what we do, take that 1 to the other side and this negative term to the other side, so we'll get the 3 minus 1 and this negative term to the other side which is the entire positive term. Okay, that means sin square alpha plus sin square beta plus sin square gamma. Okay, this one is our next term here. Okay, so 3 minus 1 can be written as a 2 and remaining term here sin square alpha, okay, plus sin square beta plus sin square gamma. Okay, third we have here sin square gamma here. Okay, this one is our required state proof of our given example. Okay, this one is our required proof. Now see that how easy type of the solutions are coming in your exam. Okay, just we have to apply only some of the basic result here for finding the solution. At the beginning what we have done here, we have taken sin square alpha, cos square alpha plus cos square beta plus cos square gamma which is equal to 1, which is an important theorem. Okay, and within that result we go for gone through some of the adjustment like sin square theta plus cos square theta which is equal to 1. We applied that result in our proof and then we land here on our required statement. Okay, So I'm expecting that you all have understood everything from this solution. Okay, now let's move for the next example. Okay, so we'll go for the next example here. Okay, in our next example we have given, if a line makes an angle 90 degree, 135 degree, 45 degree with x, y and z axis respectively. Okay, what we have here, if a line, if lines, okay, we have line given here. If line makes an angle, if line makes an angle 90 degree, 135 degree and 45 degree. Okay, we have line which makes an angle 90 degree, 135 degree and 45 degree with x, y and z axis. Okay, we have given this condition with x, with we have given condition with x axis, comma y axis, comma z axis. Okay, okay, so what we have here, basically we have a single line which in our xyz plane. Okay, so if it is in a xyz plane, that means the line obviously makes an angle with respect to x axis, with respect to y axis and along with respect to z axis. Okay, okay, so we have the angle which we line makes with respect to x, y and z. Okay, consider this one is the angle as alpha, beta, gamma. Okay, name it by some thetas like a variable. Okay, so I will name this one as alpha as a 90 degree, beta as a 135 degree and gamma as a 45 degree. Okay, so we have three of these angles here. Okay, and we know that one of the standard theorem from vector. Okay, so which is a direction ratio, direction cosines, important for the finding the direction cosines for our statement. Okay, for finding the direction cosines, we know that L square plus M square plus N square, which is equal to 1. Similar type of the result we use here. L can be defined as cos of alpha, M can be written as cos of beta and N can be written as cos of gamma. Okay, so L, M and N, these three L, M, N are the required direction cosines. Okay, L, M, N are the required direction cosines here. So this here first direction cosine, second direction cosine and this third direction cosines here. Okay, so we have to find out the three of these direction cosines. Okay, so let's move for the next part of the solution. Yes, so L which is equal to cos alpha. Okay, L which is equal to cos of alpha means cos of, what is the value for alpha, which is 90 degree. Okay, this one is our required answer. Okay, and we know that cos 90 degree, cos to 70 degree on imaginary axis always goes to the 0. Okay, and cos 0 degree, 360 degree, which always goes to 1, and cos 180 degree, it gives us the value -1. Okay, so need to remember all these value. Similarly, all the values for opposite value, it goes for the sign. Okay, yes, L which is equal to cos alpha, that means cos 90 gives us a 0, that means this one is a 0. So we got the value for L which is equal to 0, which is our first direction cosine. Okay, this one is our first direction cosine. This one is our first direction cosine. Let me write this one again. This one is our first direction cosine. Let's go for finding the second direction cosine. Okay, M which is equal to cos, N which is equal to cos gamma, take it directly. Okay, M which is equal to cos of gamma. Cos of gamma. Okay, and value for gamma we have here 45 degree. Okay, that means N which is equal to cos of 45 degree. And we know that cos 45 degree, sin 45 degree always gives us value 1 by root 2. Okay, so we get the cos 45 degree as 1 by root 2 here. Okay, So this one is our next direction cosine n, which is equal to 1 by root 2. Okay, so we got the second direction cosine as a 1 by root 2. So why I have taken that 45 degree first? Because beta, which is a 135 degree, and we know that only the we are familiar with only standard values from our trigonometry, like a 0 degree, 30 degree, 45 degree, 60 degree, 90 degree, 180, 270 and 360. These are the standard values for our trigonometric. Okay, so we all are good familiar with these conditions. Okay, so these are the easy angle that we can remember, but whenever it comes to the part of like a 135 degree or like 145 degree, which are the non-standard angles, so in such a case we have to apply some of the trigonometric result here. Okay, so basically I prefer to use the standard trigonometric result as allied angle. Okay, so if we use allied angle, then we can write easily the value for 135 degree. Okay, so let's go for finding the cos the value for m which is equal to cos beta. Okay, m which is equal to, we want the cos beta here. Okay, m which is equal to cos of beta. Okay, and what is the value for cos of beta here? Cos of beta. Okay, and the m which is equal to cos of beta means cos of value for beta, which is a 135 degree. Okay, cos of 135 degree. Okay, and 135 can be written as addition with some standard angle, like a 90 plus some theta or 180 minus some theta. Okay, something theta. So that way you have to define this one. Okay, so we can write cos of 90 degree plus 45 degree. Okay, cos of 90 degree plus 45 degree can be written as cos 135 degree. Okay, so I have written cos 135 degree as a cos 90 degree plus cos 45 degree. Okay, now using allied angle you can define the value here. Okay, cos pi by 2 plus theta. Okay, this one is also good way to find out the answer. But if you don't know the allied angle, then how can you deal such a conditions? Okay, so in this case, what you need to do, you have to use some result like a cos of a plus b, like a cos a cos b plus sin a sin b. Okay, these types of the result you have to use it here. Okay, cos a cos b minus sin a sin b. So you may use directly this result here, or apply the allied angle for finding the answer. Okay, so here we can see that I'm going to use allied angle here. Okay, I'm going to use allied angle here. Okay, and we know that allied angle can be written as cos pi by 2 plus theta. Okay, cos of pi by 2 plus theta can be written as, now see that how can we write cos of pi by 2 plus theta? We know that in our second quadrant cos gives us the negative value, because in our second quadrant cos and sine and cosec both are the positive here. In third quadrant cot and tan, and in fourth quadrant we have cos and the sec both are the positive. Okay, other than this trigonometric ratio we always get the negative other one. Okay, and in first quadrant all trigonometric ratios are positive. Okay, now here in our condition we have cos pi by 2 plus theta here. Okay, that means pi by 2 plus theta means it goes to the second quadrant. We are adding some thetas in our 90 degrees, so it goes to the second quadrant. And we know that in our second quadrant cos always gives us the negative value, so it always extract us the negative value. So write down the negative. Next condition, whenever we have pi by 2, 3 pi by 2, we convert pi by 2, 3 by pi by 2 when we have sine into cos, cos into sine. Okay, similar like that, similar like tan into cot, cot into tan, this way, and sine into cosec, cosec into, this way you have to find. Okay, so cos into cos can be converted into the sine. Okay, so we can write it as the sine for the odd angle like a pi by 2, 3 pi by 2. Okay, and the theta remains same. Okay, whenever we have cos pi by 2 plus theta, we can write it as the minus of a sine theta. This one is a standard allied angle. Okay, okay, so this one is standard allied angle. Now applying cos pi by 2 plus theta, that means cos 90 plus 45. Okay, so we can write cos 90 degree plus 45 degree can be written as minus of a sine 45 degree. Okay, minus of sine 45 degree, and we know that minus of sine 45 can be written as minus of 1 by root 2, which is the value for m. Okay, This one is the value for m. So we got the three of these different value, which first is here m, again n, and this is a l. Okay, l, m and n, three of these are required direction cosines for our given angle xyz for our line. Okay, line which intersect xyz. Okay, so I hope you all have understood this solution. Nothing we have here. Okay, just need to apply some of the basic concept for finding the solution. Okay, so let's move for the next solution, next example. Okay, so in our next example, we have to find out the direction cosines of the vector. Okay, so what we need to find here, we have to find. Okay, let me change the color. It's not that visible. So we have to find out the direction cosines of the vector. Okay, we have to find out the direction cosines of the vector. Okay, we have to find out the direction cosines of the vector. Okay, and vector we have given I cap plus 2 times j cap minus 2 times k cap. Okay, so we have given vector I cap plus 2 times j cap minus 2 times k cap. Okay, so here we can see we have given the vector and we have to find out the direction cosines for our vector. Okay, now what we do here, first of all we define here direction ratios for our vector. Okay, using our given vector. Okay, so using this vector we will define first direction ratios. Okay, direction ratios of given vector. Okay, so what we have direction ratios for our given vector, which is the first coefficient of I cap, second coefficient of j cap, and third coefficient of k cap are the required direction ratios for our given vector. Okay, so first coefficient what we have here, which is the first one. Okay, the coefficient of I cap, which is a 1. Similarly, coefficient of a j cap, which is a 2, and similarly coefficient of a k cap, which is a -2. Okay, so that means we consider, we name them as a which is equal to 1, b which is equal to 2, and c which is equal to -2. Okay, these three are the direction ratios for our given vector. Okay, now we have to work for the direction cosines. So in order to find out the direction cosines of a given vector, we have to define some of the standard result here. Okay, so what that result says that here. Okay, so we can write that result as a upon, for direction cosines we have to find out the direction cosines, means that means we have to define the coordinate for x, coordinate for y, and coordinate for z. Okay, so we can write a upon square root of, okay, we can write this one is as, let me rough with it out. Okay, let me change here. Yes, okay, square root of a upon a square plus b square plus c square comma b upon square root of a square plus b square plus c square, and third direction cosine c upon square root of a square plus b square plus c square here. Okay, three of these are the direction cosines for our given vector. Okay, now put the value for ABC in our given result, that you will get the three different direction cosines. Okay, now a upon square root of a square plus b square plus c square, that means a which is equal to 1 upon square root of 1 square plus 2 square minus 2 square. Okay, so we write 1 square plus 2 square plus minus of a 2 bracket square. Okay, so we are taking, what we are doing here, we are taking square for each and every direction ratios. Okay, 1 upon a square plus b square plus c square. This one is our first direction cosine. Similarly, go for the second direction cosine, so which is just 2 upon square root of 1 square plus 2 square plus minus of a 2 bracket square. Okay, this one is our second direction cosine. Okay, and the third direction cosines here. Okay, third direction cosine can be written as -2 upon square root of 1 square plus 2 square plus of -2 bracket square. Okay, minus 2 square, okay, plus minus 2 bracket square, okay. This one is our required direction cosines, okay. Now let's go for the finding further calculations, okay. Just we can see that it seems like that 1 square plus 2 square plus minus of 2 square, it gives us the positive 9 square root, okay, square root of positive 9, and a positive 9 which is a perfect square for 3, okay. So we can take a square root of 9 as a 3, okay. So we can write next step as a 1 upon square root of 9, okay. So addition for all of them is 9. So 2 upon square root of 9, and third one is a minus 2 upon square root of 9, okay. Go for our next calculation. We can write it as the 1 by 3, 2 by 3, and minus 2 by 3, okay. These three are the required direction cosines for our line, okay. So what we have the direction cosines for our line? First direction cosine which is a 1 by 3, second direction cosine which is a 2 by 3, and third which is a minus 2 divided by 3. These are the three required direction cosines for our given vector, okay. So what I have done here, basically by using our given vector, I define here the direction ratios. Once I get the direction ratios, I substitute all these values in our given standard theorem that it defines us the direction cosine for our given vector, okay. So I'm expecting that you all have understood. Let's move for the next solution. So in our next example, we have to find the direction ratios of the vector perpendicular to the two line whose direction ratios are given, okay. Okay, so what we want here, direction ratios of the vector perpendicular to the line, okay. So what we have claimed here, you all need to understand what we need to find, okay. Our claim, it says that find the direction ratios of the vector perpendicular to the line, okay. Find direction ratios, okay, of a vector, find the direction ratios of a vector perpendicular to line, okay. Perpendicular to line, okay. So this one is the condition. We have to find it out here, okay. Perpendicular to the line, and the line we have given, the line having vertices like a 2, minus 2, 1, minus 1, and minus 3, 4, 1, okay. So which is having first vertices minus 2, 1, and minus 1, and second vertices minus 3, minus 4, and 1, okay. These two vertices we have given here, okay. And we want the direction ratios of a vector perpendicular to this line, okay. Yes, and when we have to find out the direction ratios, okay, direction ratios for our given perpendicular line, that time we have to define some another important theorem from our vector, okay. So let's define this theorem first, okay. We will see which is the most suitable theorem for finding the direction ratios for our perpendicular line, okay. So we know that if we want the direction ratios for our perpendicular line, so we can write it as the A upon determinant of B1 C1 B2 C2, okay. Similarly, minus B upon determinant of minus B upon determinant of A1 C1 A2 C2, okay, and which is equal to C upon divided by C upon determinant of A1 B1 A2 B2, okay. This one is our required standard result for finding the direction ratios of our perpendicular line, okay. These are very much important results here for finding the solution of our given example, okay. Now what we do, first of all, we want the value for A1 B1 A2 B2 A3 B3 here, okay. So for defining this value, first of all, define our direction ratios in the form of, given direction ratio is in the form of A, B, and C, okay. So you will get the coefficient for A1 B1 A2 B2 A3 and B3, okay. Okay, let's define the direction ratios for our given line, okay. So first direction ratio, using first one, we can write minus 2 1 minus 1, we can write it here, minus 2 times A plus B minus C, which is equal to 0, okay. Using our first vertices, I have written minus 2a plus b minus c, which is equal to 0. Similarly, introduce ABC here in our second vertices. Okay, so minus 3 times a minus 4 times b plus c, which is equal to 0. Okay, these are the two required given lines from our given direction ratios. Okay, now compare the values and find out the value for a, b, c here. Okay, so we can see here a1a, b1b, c1c, which is equal to 0. So we get the value for a1, which is a minus 2, again b1, which is equal to 1, and c1 we have here minus 1. Okay, so minus 2, 1, minus 1, all are the value for a1, b1, c1. Similarly for a2, which is a minus 3, b2, which is a minus 4, and c2, which is here a2, b2, c2, which is here 1. Okay, these all are the value for a1, b1, c1, a2, b2, c2. Now substitute all these values in our given result. You will get the required direction ratios for our perpendicular line. Okay, yes, put the value. So as we don't have the value for ABC, so keep that value as it is, because these are the required direction ratios for our perpendicular line. Okay, so keep that as it is here. Okay, now let's go for substitution of the value and further calculations. So a upon, we have determinant b1, c1, b2, c2. Okay, so b1, c1, b2, c2. 1 minus 1 minus 4, 1. Okay, 1 minus 1 minus 4, 1, which is our 2 by 2 determinant. Okay, 1 minus 1 minus 4, 1, which is equal to minus of b. So what is the minus of b here? Keep as it is, minus of b. We don't know the value for minus of b. So okay, minus of b completely divided by a1, c1, a2, c2. Okay, so a1, c1, a2, c2. So minus 2, minus 1, minus 3, 1. Okay, minus 2, minus 1, minus 3, 1. And c upon a1, b1, a2, b2. Okay, a1, b1, a2, b2. So minus 2, 1, minus 3, minus 4. So minus 2, 1, minus 3, minus 4. Minus 2, 1, minus 3, minus 4. These are all are the values for our given determinant. Go for the next calculations. Okay, so keep a as it is at the denominator. 1 ones it keep as it is 1. Okay, minus of minus 4 into minus 1, it goes to the plus 4. Okay, so minus of 4, it comes here, a upon 1 minus 4, which is equal to minus b divided by minus 2 upon minus 3. Okay, which is equal to c completely divided by minus 2 into minus 4, which gives a positive 8, minus of minus, which goes to the plus 3. Okay, these are the value for a upon, b upon, and c upon here. Okay, so go for finding the next step. A upon 1 minus 4, so we can write a upon minus 3, which is equal to minus b upon minus 2 minus 3, we can take minus 5. Okay, and c upon 8 plus 3, which is a 11. Okay, so we can write a upon minus 3, b upon 5, and c upon 11. Okay, so that means the value for minus 3, 5, and 11, which define our required direction ratios for the line. Okay, so our direction DRS of our perpendicular line. Okay, of our perpendicular line, which is a minus 3, 5, and 11. This one is our required answer here. Okay, direction ratios for our perpendicular line. Now see that how easy type of the solutions are there. Okay, I'm expecting you all have understood this solution. Okay, even after you found anything difficult, let me know in my comment section. I will come up with the similar videos. Okay, so now let's move for the next question. Okay, so in our next question, we have to find it out the direction cosines of the line perpendicular to the line whose direction ratios are given. Okay, so similar examples like a previous one, but we have extended this example to the direction cosines. First of all, we have to define the direction ratios for our perpendicular line, and then we will go for defining direction cosines for our line. Okay, okay, let's go for finding the direction cosines and direction ratios. Okay, first of all, find out the direction ratios for our perpendicular line. Okay, once you get the direction ratios, then it is easy to find out the direction cosines. Okay, okay, the vertices for our direction ratios. Okay, direction. Okay, okay, for direction ratios. Okay, direction ratios for the perpendicular line using vertices -2, 1 and -1, and second vertex is -3, -4 and 1. Okay, these two are the vertices we have here, first and second here. Okay, now introduce the another variable like ABC, that is helpful for finding the direction ratios. Okay, so we can write -2 times A plus B minus C, okay, which is equal to 0, which is our first equation using our given first direction ratio. Okay, so using second direction ratio, -3 times A minus 4 times B plus C, which is equal to 0. Okay, these are the two direction ratios. Okay, using this we can write the value for A1, B1, C1. Okay, A1, B1, C1. So what is the value for A1, which is a minus of a 2, okay, B1 which is a 1, and the C1 which is equal to minus of 1. Okay, so A1, B1, C1. Similarly for A2, B2, C2. A1, B1, C1. Okay, similarly for A2, A2 is here -3, B2 which is here -4, and C2 which is here 1. Okay, see that -2, 1, -1, -2, 1, -1, and -3, -4, 1. Okay, -3, -4, 1, which are given the value for our required direction ratios. Okay, so using these direction ratios, find out the direction ratios for our perpendicular line. Okay, and we know that for the finding direction ratios of a perpendicular line, we define the value as using our standard form. Okay, so we can write it as the A upon determinant of B1, C1, B2, C2. Okay, which is equal to B upon determinant of A1, C1, A2, C2. Okay, which is equal to C upon determinant of A1, B1, A2, B2. Okay, this is A1, B1, A2, B2. This one is our standard form for finding the direction ratios for our given perpendicular line. Okay, so whenever we have perpendicular line, that time apply this result. Okay, so put all these values. So we can write A upon a determinant of, okay, we can write A upon determinant of, what is the value for determinant? B1, C1, B2, C2. Okay, so B1, C1, B2, C2. 1 minus 1 minus 4, 1. Okay, 1 minus 1 minus 4, 1. Okay, 1 minus 1 minus 4, 1. Okay, A upon B1, C1, B2, C2. So B upon, so we have here a negative sign for our B here. Okay, which is a negative sign. We have to take positive, negative, positive, negative, alternate sign there. Okay, yes. So B negative of a B upon, so we have 2 by 2 determinant here. Okay, B upon what we have? A1, C1, A2, C2. So -2, -1, -3, 1. Okay, -2, -1. Okay, -3, 1. Okay, this one is minus B upon. And third, C upon, okay, C upon 2 by 2 determinant, A1, B1, A2, B2. A1, B1, A2, B2. So -2, 1, -3, -4. Okay, -2, 1. Okay, -3 and -4. Okay, these are the three determinant for A upon, B upon, and C upon here. Okay, let's go for finding the values directly. Okay, so A upon, we can take it as the value for determinant 1 minus of a -4. Okay, minus of 4 into -1, it goes to the positive 4. Okay, so 1 minus 4 can be written as -3. Okay, A upon -3 minus B divided by -2 upon -3. Okay, so -2, so keep it as -2 as it is, and -1 -3, it is a positive 3, -3 we can write it is here, which is equal to C upon -2 into -4, which is a positive 8, and minus of -3, which is a positive 3 here. Okay, so we can write A upon -3, which is equal to minus B upon -5. So we can write it as the B upon 5 directly. Okay, and C upon 8 plus 3, 11. Okay, C upon 11 here. These are our required direction ratios for our given line. Okay, So our required direction ratios of our given line, okay, -3, 5 and 11. Using these values, try to define the value for A, B and C, okay. Okay, so the value for A, B, C, we can take A which is equal to -3, B which is equal to 5, okay, and C which is equal to 11, which are the required direction ratios, okay. And for finding the direction cosines of the line, okay, for finding the direction cosines of the line, we know that we use the result A upon square root of A square plus B square plus C square, which is the first direction cosine. Second, B upon square root of A square plus B square plus C square, which is the second direction cosine. And C upon square root of A square plus B square plus C square, which is a third direction cosine we have here, okay. Now substitute all these values and go for finding the calculations, okay. Okay, so next, put the value for A, which is a -3 upon A square plus B square plus C square, -3 square plus 5 square plus 11 square, okay. So -3 square plus 5 square plus 11 square, okay. This one is our first direction cosine. Similarly, 5 upon square root of -3 square plus 5 square plus 11 square here, okay. So this one, consider this one is a denominator here. And third direction cosine, C upon, okay. So 11 upon -3 square plus 5 square plus 11 square, okay. So this one is our third direction cosines. Go for finding the calculation, you will get the required answer here, okay. Okay, so here we can see that -3 upon -3 square, 5 square, 11 square. 11 square which gives us 121. 3 square which gives us a 9. So 121 plus 9 which is 130. And 130 plus 5 square 25. Okay, so 155. So we will get the first direction cosine as a square root of 155. Okay, -3 upon square root of 155. Second direction cosine, as we have denominator same everywhere, so square root of 155 will remain same. Okay, so 5 divided by square root of 155. Okay, and third direction cosines we have 11 divided by square root of 155. Okay, so these three are our given required direction. These three are our given required direction cosines for our given line. Okay, so you can name it as the L, M, N. This one is a L, this one is M, and this one is a N. Okay, you can name these as a L, M, N as the direction cosines for our given line. Okay, so I'm expecting that you will have understood this solution. Okay, nothing we have here. First of all, we have to define direction ratios from our given vertices, and using condition for perpendicularity, so we apply here one important result, and at the end I found the direction ratios by using this, and using the direction ratios proceed with the direction cosines. Okay, now let's move for the next question. In our next question, we have given a line drawn from the point A which is a perpendicular to point P and Q, and find the coordinate of the foot of perpendicular. Okay, so what we have given, a line drawn. Okay, so we have the line which is drawn from the point A, okay, which is the perpendicular here, okay, which is the perpendicular here to the point P and Q. Okay, so point P it is here, point P Q it is here. Okay, and the point vertices we have here A which is having coordinate 1 2 1, P which is a 1 4 6, okay, and Q which is a 5 4 4. Okay, 5 4 4. Okay, this is our required data in our example. I just drew it in the form of a figure, okay, in order to understand it better. Okay, now we can see that our A, which is a perpendicular to the line segment joining point P and Q, then we want the coordinate for the foot of perpendicular. So we want the coordinate for here. Okay, we want the coordinate for the foot of our perpendicular. Okay, now consider this one as the B. Okay, so that means we want the coordinate for our foot of point B here. Okay, now we can see that as we don't have their ratio PB and BQ, is they are equal or not equal, so in such a case, don't apply directly midpoint formula, apply always the section formula for internal division, because the point B divides our line segment PQ internally. Okay, so apply the section formula for internal division. Okay, so for that we have to consider say their ratio as a lambda as to 1 here. Okay, their lambda as to n, as we don't have the ratio, so consider always their ratio as a lambda as to 1. Okay, Then you will understand the next procedure. Okay, so I consider their ratio as a lambda is 2, and let's go for the defining the coordinate for the point B. Okay, so by using internal section formula for internal division, we write m a bar plus n times b bar upon m plus n, which is a section formula for internal division whenever we have two position vector or two vertices here. Okay, but in our figure we have given three coordinate like x coordinate, y coordinate and z coordinate. So we have to define the section formula separately for these three coordinates. Okay, so now let's go for the defining the section formula for three of these coordinates separately. Okay, yes, so we can define 5 times this lambda, 1 times this 1 upon lambda plus 1. Okay, which is the first coordinate. What it is the first coordinate? 5 times lambda plus 1 upon lambda plus 1, which is the first coordinate. Similarly, 4 times lambda plus 4 times lambda plus 4. Okay, so we can see here 4 times lambda plus 4 divided by lambda plus 1. Okay, and third coordinate lambda 4 times lambda plus 6 times 1, which is a 6 divided by lambda plus 1 are the three coordinate for our point B. Okay, these are the three coordinate from our point B, as we have the section formula for internal division and it divides our line segment internally as the lambda as to 1. Okay, now we can see that how I have applied the section formula for internal division. So first coordinate in the into the first ratio here P to B, which I consider lambda. Similarly, first coordinate into the second ratio here, which is 1 upon lambda plus 1 here. Okay, and we have to define the value for lambda here using our given data. Okay, yes, so these are all are the vertices here for our point B here. Okay, for point B, which are the coordinates for x coordinate, y coordinate and z coordinate here. Okay, so we have to find out the here value for lambda, and then we can easily define the direction ratios for our point B here. Okay, so we can easily define direction ratios for our point B. So for finding the value of a lambda, we go through using their vertices 1 to 1, and B here we consider some another vertices, and then we find here vector which passing from our perpendicular line here. Okay, then let's proceed with the value then. Yes, okay, so we want the direction ratios here. So what we do here for finding the direction ratios, we can write 5 minus 1, 4 minus 4 and 4 minus 6 here, which are the direction ratios for our line segment PQ. Okay, for line segment PQ, we can find the direction ratios easily. Okay, 5 minus 1, which is the first direction ratios, second 4 minus 4, which is the second direction ratios, and third direction ratio 4 minus 6. Okay, 4 minus 6. So 5 minus 1, which gives us 4. 4 minus 0, which gives us 4. Okay. Okay. No, not a 4 minus 0, which is 4 minus 4. Okay. So we have given, we can see here 4 minus 4 it is there, not a 0. Okay. So 4 minus 4, which gives us the value 0. And third 4 minus 6, which gives us the value minus 2. Okay. These are the direction ratios for this line segment here. Okay. And the direction ratios for this AB, we have here these three coordinates. Okay, now we can write the linear combination for these two direction ratios with a given values vertices for x, y, z for point B here. Okay, now take their linear combination for these two vertices. Okay, so we can write this one as 4 multiplied by first vertices, 0 multiplied by second vertices plus third to minus 2 multiplied by third vertices, which is that linear combination for our direction ratios with the vertices here. Okay, so multiply 4 into our first one. So 4 multiplied by under bracket 5 lambda plus 1 divided by lambda plus 1. Okay, this one is the first, again plus 0 times second here vertices here, second coordinate for y, 4 lambda plus 4 upon lambda plus 1 here. Okay, and at the end minus 2 times last one. Okay, so minus 2 times last the coordinate for z, so which is a 4 lambda plus 6 upon lambda plus 1 here. Okay, these all are the three vertices here. So 0 into this, it goes to 0. So 4 into this, minus 2 into this one here. Okay, okay, so let's go for the next part. Okay, so 4 multiplied by this one, so we can write which is equal to 0 we have here. Okay, so we have equal to means what we have here, the linear combination for first vertices is the first here plus second linear combination plus third linear combination, it goes to the 0 here. Okay, now 4 multiplied by, go for the multiplication, 4 5s are 20 lambda, so we can write it as the 20 lambda plus 4 total divided by lambda plus 1, yeah, it is there. Okay, so 0 multiplied by second one, it always goes to 0. As we know that when we multiply 0 vector to the any vector, it always gives us the 0 value. Okay, so let's multiply negative 2 to the another one. So 4 2s are 8 lambda, so which is 8 lambda, and 6 2s are 12. Okay, plus 12 under bracket, keep 8 lambda plus 12 upon lambda plus 1 here. Okay, this is the subtraction between these two one, because negative sign out here, which is equal to 0. Just go for finding the value for lambda here. Okay, just need to find out the value for lambda. Okay, so for finding the value for lambda, we have denominator lambda plus 1, similar, take it once, add their numerator, then you will get the required answer here. Okay, okay, so let's go for finding the value then. Okay, so 20 lambda plus 4 minus 8 lambda minus 12. Okay, so 20 lambda plus 4, okay, 20 lambda plus 4, my negative multiply under bracket, minus 8 lambda minus 12. Okay, and so completely divided by lambda plus 1, it is both the denominator we have same, we take it once here. Okay, so 20 lambda minus 8 lambda can be written as 12 lambda. Okay, 12 lambda, 20 lambda plus minus 8 lambda, which is a 12 lambda, and plus 4 minus 12, we can write it as the minus 8, which is equal to 0 here. Okay, so lambda plus 1, take it to the other side, it goes to obviously 0. Okay, okay, so 20 lambda minus 8 lambda. Okay, so 20 lambda minus 8 lambda, which is a 12, and 4 minus 12, which gives us a minus 8 here. Okay, so what we do, take 4 common here, 3 lambda minus 2, which is equal to 0. Okay, so we get this value here, 3 lambda plus 5. Okay, so what we have next vertices here, 4 lambda plus 6. Okay, 4 lambda plus 4 times lambda plus 6 here. Okay, 1 4 6 is there, 1 4 6 5 4 4. Okay, these three are the vertices we have here. Okay, yes, 3 lambda plus 5 here. Okay, upon lambda plus 1, yes, 1 4 6. Okay, 5 4 4. Okay, 1 4 6 5 4 4. Okay, these are the 3 vertices we have here. Yes. Okay, so what we do here, first of all, we are going to take the subtraction between these vertices. Okay, then we will get the required answer here. Okay, so what we do, first of all, we are going to subtract the direction ratios from our line segment AB. Okay, so we did not subtracted the direction ratios from our given line segment. Okay, so we have to subtract here the direction ratios first. Okay, direction ratios from our line AB. Okay, which we will get the required answer. That means we have to subtract from 1, 2 and minus 1, then you will get the direction ratios for our line segment AB. Okay, so I have taken directly the vertices at point B. So we do not want the vertices at the point B, we want the direction ratios from vertices A to vertices B. So what we want here, okay, so we want here, we want the subtraction from this one with the 1 minus 1 minus 2 minus 1. Okay, that part is left here, so we have to find out this part first and then we go for multiplying their answer. Okay, so that's why we are taking directly their steps as a direction ratios, but we do not want that step as a direction ratios. Okay, so for this, what we do, we first of all find out the direction ratios for our given line segment. We do not want the vector here. Okay, so we want the direction ratios for our line segment. Okay, so direction ratios for point A to point B, we can write it as the 5 lambda plus 1 upon lambda plus 1 minus 1. Okay, so 5 lambda plus 1 upon lambda plus 1 minus 1, which is the first direction ratios using this one. Similarly, second direction ratios, 4 lambda plus 4 upon lambda plus 1, 4 lambda plus 4 upon lambda plus 1 minus of 2, say, which is the second direction ratios. Similarly, 4 lambda plus 6, 4 lambda plus 6 upon lambda plus 1 minus of 1. Okay, these three are the given direction ratios for our line segment AB. Okay, so we do not want the only vertices or coordinate for B as a XYZ. We want the direction ratios for our line segment AB. So what I have done in my previous part, by mistakenly I taken directly as a point B here as a direction ratios. Okay, so we do not want the only point for our B, so we want our for line segment AB. Okay, so go for the subtraction and we will get the value 4 lambda. Okay, 5 lambda plus 1, multiply this into this minus this, you will get the next value. Okay, so 4 lambda, their subtraction, you will get the lambda plus 1. Second direction ratios we will get here. Okay, just need to subtract these values. Okay, so lambda plus 1 into minus 1 plus 5 lambda plus 1 upon lambda plus 1 is our first value. Okay, so we will get the 2 lambda plus 2 as a second value. Okay, so you have to go for the calculation. This is just a part of a calculation. Okay, 2 lambda plus 2 upon lambda plus 1. And the third direction ratios we have here 3 lambda plus 5. Okay, so after calculation of this 3 lambda plus 5, we will get our third direction ratios here. Okay, so all these three values we have here. Now take the linear combination of these direction ratios with the 4 0 minus 2. Okay, so this multiplied by 4, this multiplied by 0, minus 2 multiplied by this one. Okay, now let's move for the next step. Okay, so next step you can write 4 multiplied by under bracket 4 lambda upon lambda plus 1. Yes, first one, plus 0 times the second, 0 times second vector, it always goes to the 0 vector, and minus times, so last one we left here, so plus 0, keep it is 0, minus times last vector, minus 2 multiplied by 3 lambda plus 5. Okay, 3 lambda plus 5 divided by lambda plus 1, which is our required third direction ratios. Okay, now go for the calculation of finding their values. Okay, so you will get the value as a 10 lambda minus 10, which is equal to 0. Okay, so 10 lambda minus 10, which is equal to 0, we will get here 10 lambda minus. So these are the quite bit calculation base part. So that's why I'm skipping there. 10 lambda minus 10, which is equal to 0. Okay, so lambda plus 1, lambda plus 1, it goes to 0. So 4 lambda into 4 lambda, 16 lambda minus 2 3s are 6 lambda plus minus of 10. Okay, so you have to go for the just calculation. So we will get the lambda which is equal to 10, 10 upon 10, we will get the lambda which is equal to 1 here. Okay, so I got the lambda which is 1. Put that lambda here in our given direction value. Okay, the value which we have here 5 lambda plus 1, 5 lambda plus 1, lambda plus 1, 4 lambda plus 4, and lambda plus 1, 4 lambda plus 6, and lambda plus 1. Okay, substitute lambda here, you will get the coordinate for our point B. These are the coordinate for our point B. Okay, so you don't have to substitute at downside here on or in other equation, because we want the coordinate for our foot of our perpendicular. Okay, so coordinate for our foot of perpendicular, these are here. Put the value for lambda 1 here everywhere, so we will get the required answer. Okay, so 5 into 1 plus 1, which is a 5 into 1 plus 1, which is a 6. We will get the 6 as the numerator. Lambda plus 1, that means it is a 2, which is next one we have here 6 by 2. Okay, first one is the 6 by 2. Second one is 4 lambda plus 4, that means 4 plus 4, 8 divided by 2. Second one is 8 divided by 2. And third one 4 lambda plus 6, that means 10 divided by 2, which is our third foot of our coordinate. Okay, so 6 by 2, which is a 3, 8 by 2, which is a 4, and 10 by 2, which is a 5. These three are the required foot of our point B here. Okay, so I'm expecting that you all have understood this solution. It's just an easy part, need to follow the process only here. Okay, let's move for the next question. We have to find out the direction ratios of the line which perpendicular to the line with the direction ratios are given. Okay, so similar type of the example already we have solved it here. Okay, but still we are going to go for this solution. Okay, so we have to find out the direction ratios of a line. Okay, we want the DRES, direction ratios of a line. Okay, we want the direction ratios of a line which is perpendicular to the line with a direction ratio. Okay, so we have the direction ratios of a line which is a perpendicular. Okay, which is a perpendicular to the coordinate 1 3 2. Okay, which is the first one. Second one minus 1 1 2. Now introduce the value for A, B, C here, as we want the direction ratios for point A, B, and C. So we can write A plus 3 times B plus 2 times C, which is equal to 0, and minus A plus B plus 2 times c, which is equal to 0. So we can write the value for a1 b1 c1. Okay, we can write the a1 b1 c1 by using this one. So a1, which is a 1, comma, b1, which is a 3, comma, c1, which is equal to 2. Okay, so similarly a2 which is a -1, b2 which is equal to 1, and c2 which is equal to 2 here. Okay, a1 b1 c1, a2 b2 c2, all are the coordinate we have here. Yes. Okay, now let's go for the next part. a1 b1 c1, a2 b2 c2 we have here. Let's, in our next part, what we do, we are going to find out the direction ratios. So for this, we know the result. We can write a upon determinant of a1 b1 c1 b2 c2. Okay, so b1 c1 b2 c2 under determinant here, b1 c1 b2 c2. Okay, this one is a upon this one. So b upon, okay, so c1 a1 c1 a2 c2 here. Okay, similarly c upon, so it is a negative sign, it is coming for b, c upon a1 b1 a2 b2 here. Okay, these three are the values here. Now let's go for the substitution of the value. You will get the required answer. Okay, okay, so in our next step, keep a as it is because we want the direction ratios. b1 c1 b2 c2. Okay, what is the b1 c1? 3 2 1 2. Okay, 3 2 1 2, 3 2 1 2, which is here the value for b1 c1 b2 c2. Similarly minus b upon a1 c1 a2 c2, a1 c1 a2 c2, 1 2 minus 1 2. Okay, 1 2 minus 1 2 here upon minus b upon this one, and a c upon third determinant. Okay, a1 b1 a2 b2. Okay, so 1 3 minus 1 1, so 1 3 minus 1 1 here. Okay, so this is our third determinant here. Okay, so we can write their value as a upon the determinant 3 to the 6 minus 2, which is a 4, a upon 4, which is equal to minus b divided by 2 minus of minus 2, which is a b upon 4 minus b upon 4. Okay, 2 minus 2 minus of minus 2, which is 4, and which is equal to c upon, we can write here 1 minus of minus 3, which is a 4. Okay, so we can write a upon 4, b up minus b upon 4, and c upon 4. Okay, so our required direction ratios here 4 minus 4 and 4 for our given perpendicular line. Okay, so required direction ratios, then we can write, which is 4 minus 4 and 4. Okay, these three are the required direction ratios for our given line. Okay, so that's it we want in our example. I'm expecting that you all have understood this solution. Nothing it is difficult here. Similar type of the example I already explained here. Now let's move for the last example. Okay, so we have to find out the volume of a tetrahedron. Okay, whose vertices are a, b, c and d. 4 vertices are given, a, b, c, d vertices are given, and we want the volume of our tetrahedron. Okay, so volume of a tetrahedron can be written as using 4 vertices as, let me write the volume of a tetrahedron. Volume of a tetrahedron, which can be written as using the vertices a, b, c and d, we can write it as the a, b, a, c and a, d. Okay, so 1 by 6 a, b, a, c and a, d. Okay, these three are the segment like a, b, a, c and a, d. Then we can write it as the a, b, a, c, a, d as the line segment here. Okay, for finding the volume of a tetrahedron. Okay, now using this we have to define a 3 by 3 matrix. Okay, so let's go for finding the value for a, b, a, c, a, d first, then I will explain to you all the how can we define the determinant. Okay, so AB can be written as, vector AB can be written as B bar minus A bar. Okay, and vector BC AC can be written as C bar minus A bar, and vector AD can be written as D bar minus A bar here. Okay, so substitute these values here. First of all, we have to find out the value for using vertices A, minus 1 2 3. Okay, so we can write minus times I cap plus 2 times j cap plus 3 times k cap. Okay, this one is the vertices using A. Similarly, using vertices b, 3 minus 2 1. Okay, so we can write 3 times I cap minus 2 times j cap plus k cap. Okay, using vertices b. Similarly, for using third vertices, c op 2 1 3. Okay, c op 2 1 3. Put the value for I cap, introduce I cap, j cap, k cap. Similarly here for third was c. Okay, 2 times I cap plus j cap plus 3 times k cap here. Okay, so the vertices c, I have written this one. And similarly left here the value vertices d here, minus 1 minus 2 4. Okay, minus 1 minus 2 4. Using this one we can define the position vector which exists there. Okay, so minus I cap minus 2 times j cap plus 4 times k cap. Okay, these three are the position vector we have here. Now we want the value for AB, that means the position vector B bar minus position vector A bar. Okay, so we can see that the position vector B bar minus position vector A bar means we have to subtract or add similar type of the coefficient, like I with I, J with a J, and K with a K. Okay, yes, so 3 I cap, so we have here 3 I cap minus, we have to subtract them. So 3 I cap minus of minus I cap, we can write it as the 4 times I cap. Okay, similarly minus 2 j cap plus minus of minus 2 j cap, we can write minus 4 times j cap. Okay, so what we are doing basically here, we are subtracting b bar minus a bar. So minus 2 j cap minus 2 j cap. Okay, k cap minus 3 k cap, we can write minus 2 times k cap. Okay, similarly c bar minus a bar. Okay, so 2 I cap minus of minus I cap, which is minus 3 I cap. J cap minus 2 j cap, we can write minus j cap. K cap, okay, 3 k cap minus 3 k cap. Okay, so what we have here, b bar c bar minus a bar. Okay, so 2 I cap minus I cap, which is a minus 3 I cap. Okay, 2 I cap minus of minus I cap, which is a plus 3 I cap here. Okay, c bar minus a bar. Okay, 2 I cap minus of minus I cap, which is a plus 3 I cap. J cap minus 2 j cap, we can write minus j cap. Again 3 k cap minus after that c bar minus a bar. Okay, so 3 k cap minus k cap, we write it as the 0 times k cap here. Okay, similarly for d bar minus a bar, so d bar minus a bar, so minus I cap minus of minus I cap, which is a 0 times I cap. Okay, so we can see here minus I cap minus of minus I cap, which is a plus I cap, minus I cap plus I cap, it goes to the 0. Okay, 0 times I cap. Similarly minus 2 j cap minus 2 j cap plus minus of minus 2 j cap, we can write minus 4 times j cap. Okay, similarly 4 k cap minus 3 k cap, we can write a plus k cap. Okay, so here, so using all these we vector AB, AC and AD, we have to define the 3 by 3 determinant here. Okay, now see that carefully how I am define the value for our determinant. Okay, so 1 by 6 keep as it is. The AB, AC, AD can be written as AB dot AC cross AD. Okay, dot and cross product whenever we have, we take the coefficient 4 minus 4 and minus 2 here, 3 minus 1 0 and third 0 minus 4 and 1. Okay, so we have to find out the value for this determinant. I'm not going to find this value here because it's quite time taking, and I'm expecting that you all are familiar with that. How can we find the value for 3 by 3 determinant? Okay, so if you wanted to see how can we deal the 3 by 3 determinant, do check in my playlist. You will get the complete lecture series on determinant matrix chapter. Okay, so our required answer it gives us here. Okay, after finding all these answers, okay, all these values, we get the our required answer. Okay, 4 minus 4 2, just find out the answer here. So our required answer, it comes as a 16 by 3 cubic unit. Okay, so just go for finding the value 16 by 3 cubic unit. Okay, this one is our required answer for our given example. Okay, so I'm expecting that you all have understood this type of the solutions. Okay, very easy type of the solution, you always ask in your board exam. Okay, so I'm expecting you all have understood everything from my today's lecture. So at the beginning, what we have started here in our lecture, we learn direction cosines, direction ratios. We learn little recap about this. After that, coplanar vector, collinear vector. After that, we have learned some of the standard theorem. At the end, we learn section formula for internal division, external division, and based on all these topics, we solve some of the examples here. Okay, so I hope you all have understood everything from my today's lecture. Even after, if you found anything difficult, let me know in my comment section. I will come up with the similar video. So thank you everyone. Thank you for my today's lecture.